Okay, so we're going to look at section 6.3, which is double angle, power reducing, and half angle formulas. So last time we looked at the sum and difference formulas, and we're going to use those to be able to derive the double angle formulas, right? It's not too crazy, right? So like if I have, for example, sine of 2 theta, right? This would be the same thing as sine of theta plus theta. Right? So then basically u and v are equivalent, right? They're all equal to the theta. So if I plug that into the equation from section 6.2, we would have, sine theta times cosine theta plus cosine theta times sine theta. These two things are identical, right? Because of the commutative property of multiplication, right? So notice the only thing different is the order, right? So this would simplify just to be 2 sine theta cosine theta, right? I have two of the same term, right? So then we can do the same thing with cosine. So if I want to look at, well, what's cosine of 2 theta? Well, this is equal to, so again, this would be cosine of theta plus theta. And then using the sum formula, plugging in theta for u and v, this would be cosine theta times cosine theta minus sine theta, which would, be equal to cosine squared theta minus sine squared theta. Right? And then, tangent of 2 theta is equal to tangent of theta plus theta, which would be equal to, so this would be tan theta plus tan theta all over 1 minus tan theta times tan theta, which is equal to 2 tangent theta divided by 1 minus tangent theta squared. Right. So then we can come up with those with these formulas, right? So we came up with this formula, and we came up with this first formula, right? And then you can come up with the others as well. So if you want to see where those come from, if you start with the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, then I could subtract sine squared from both sides. And that leaves me with cosine squared theta equals 1 minus sine squared theta, right? And then to keep going, so if we start out with cosine of 2 theta in its form that we solve for, right? So then what I can do is I can plug in, and for cosine squared theta, I can plug this in 1 minus sine squared theta. So we'd have cosine of 2 theta equals 1 minus sine squared theta minus sine squared theta. And then, this would just simplify to be 1 minus 2 sine squared theta. Right, so that gets me the second version. And then the next version is very similar, right, except for we want to solve the Pythagorean identity for sine squared, right? So if I start with the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, I can subtract cosine squared theta from both sides, and we're left with sine squared theta equals 1 minus cosine squared theta, right? So then just like before, right, we start out with cosine 2 theta equals cosine squared theta minus sine squared theta. Then I can plug this in to here. So this would give me cosine squared theta minus 1 minus cosine squared theta. And we can simplify this, so we distribute the negative through. We'd have cosine squared theta minus 1 plus cosine squared theta, which gives me, combining like terms, 2 cosine squared theta minus 1, right, which is exactly that other version, right? So cosine of 2 theta has 2 versions in that chart. All right. So now we can use these formulas in example 1. So example 1, we have 3 parts. We're told that sine of theta equals 4/5 for theta in quadrant 2. We want to find the exact function values, right? So sine of 2 theta is equal to 2 sine theta times cosine theta. Right, so we want to be able to find sine and cosine. So if I draw a picture of this, right, then I'll just go ahead and do, all students take calculus just as a reminder, and then for the sines of the trig functions, and then remember that sine theta is equal to y over r, and cosine theta is equal to x over r. So in other words, the y value is equal to 4, r is equal to 5, right? We're told we're in the second quadrant, so we're going to be somewhere up here, right? So here's r equals 5, and then we have, x here, and then y equals 4 here. Oops. R equals 4. Wait, no, 5. Right? So then we just need to figure out what x is in order to find cosine. So, using Pythagorean theorem, we'd have x squared plus 4 squared equals 5 squared. So this would be x squared plus 16 equals 25. Subtract 16 from both sides. We get x squared equals 9. And then take the square root of both sides, we get x equals plus or minus 3. Right, so in this case, since we're in the second quadrant, my x value is negative, right? So x is negative 3. Right, so now we can just fill these in. So we'd have 2 times sine of theta, which is 4/5. Oops. Yeah, that didn't turn out very good. 4/5. And then cosine of theta is x over r, so it'd be negative 3/5. Right? So we can simplify this, and you should get negative 24/25. Right, as your solution. Actually, I'm just going to go ahead and write off to the side tangent and cosine and so forth, right? So let me just grab another color. So sine of theta, as we said, is y over r, which is equal to 4/5. Cosine of theta is equal to x over r, which is equal to negative 3/5. And tangent of theta is equal to y over x, which is equal to 4 over negative 3. Right. So we'll need these values to plug in for these other formulas, right? So cosine of 2 theta, right? So there's 3 different options you can use. So I'm just going to use the first one we did, is cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Right, so just plug in these values. So we would have negative 3/5 squared minus, and then sine is 4/5 squared. So this gives me 9/25 minus, that would be 16/25. Right, so then 9 minus 16 is negative 7, so we would be negative 7/25. Right, that's our answer there. And then tangent of 2 theta is equal to 2 tan theta all over 1 minus tan theta squared. So we can just plug in our values for tangent. So this would be 2 times negative 4/3 divided by 1 minus negative 4/3 squared. So this is equal to negative 8/3 in the top. Right, just multiply fractions. And then this would be 1 minus 16/9. So we could, instead of writing 1, we could do 9 over 9, right? So this becomes negative 8/3 divided by, that would be what, negative 7/9, which is equal to negative 8/3 times negative 9/7. Right, just dividing fractions. So this comes out to be, what, 24/7. Right, reduced. Right. So then example 2, we want to verify the following identity. We want to verify cosine of 3x equals 4 cosine of 3x minus 3 cosine of x. Right, so again, the general idea is we want to start with one side and try to come up with the other side, right? So in this case, we don't always have to start with the left-hand side, right? It just happens that the left-hand side seems to be the easiest to work with, typically how it's written, which is going to be the case for us, right? Because cosine of 3x, we can think of this as cosine of 2x plus x and use the sum formula, right? So this would be equal to cosine of 2x times cosine of x minus sine of 2x times sine of x, right? And then we know what cosine of 2x and sine of 2x are equal to, so we can substitute those in. So we could do, cosine squared x minus sine squared x times cosine of x. Then we'd have minus 2 sine x times cosine x times sine x. Right? So then now I can distribute the cosine x through, so this would give me cosine cubed x minus sine squared x times cosine x minus 2, we could rewrite this as sine squared, right? Sine squared, because I have 2 factors of sine x, 2 sine x squared cosine x. So then these two guys are now like terms, so combining those we get cosine 3x minus 3 sine x cosine x. Oops, sine squared. All right, so we're starting to get a little closer, right, to what what our goal is. So I have a cosine cubed x at least. So I'm missing this 4, and looking at this, I want to have a cosine here, but I don't want to have sine squared x here. So what we can do is try to plug something in for sine squared x, right? So using Pythagorean theorem, sine squared x plus cosine squared x is equal to 1. So if I subtract cosine squared x from both sides, we get sine squared x equals 1 minus cosine squared x. So I'm going to substitute that in for here, see if that helps get us any closer. So this would be equal to cosine cubed x minus 3 times 1 minus cosine squared x times cosine x. Right? So so distributing this through, right, what I'm going to get is cosine cubed x minus 3 plus 3 cosine squared x And this is, all times cosine x, right? So we still have this factor of, so I'm going to put, let me write it like this. I'll do minus. Just make that 3. Right. There. So we still have this cosine x being multiplied all times this, right? So now when I distribute that through, we'd have cosine cubed x minus, so cosine x times 3 would be minus 3 cosine x, and then cosine x times 3 cosine squared x would be plus 3 cosine cubed x. And then I can combine like terms. So this would be equal to, this would end up being 4 cosine cubed x minus 3 cosine x, right? Which is what we're trying to after. That's equal to the right-hand side, right? All right, so the next one's here. Objective 2 is applying the power-reducing formulas, right? So how we come up with these formulas is if we go back to the double angle formulas. Let me change this color. We're using these two that I'm highlighting in orange to come up with these what we call power-reducing formulas, right? Because we're going from like something squared down to something that doesn't have a square. So we're like going down a power, if you will. Right? So for example, if I start with the first one, cosine of 2 theta is equal to 1 minus 2 sine squared theta. Right? What I can do is try to solve this for sine squared theta. So I can subtract 1 from both sides. So we get cosine of 2 theta minus 1 equals negative 2 sine squared theta, and then divide both sides by negative 2, which gets me to sine squared theta equals, it would be 1 minus cosine 2 theta all over 2, right? So there's one of the formulas, right? So we could come over here and do the other one. So the other version was cosine of 2 theta is equal to 2 cosine squared theta minus 1. So let's solve for cosine squared. So we add 1 to both sides. So we get 1 plus cosine of 2 theta equals 2 cosine squared theta. Divide both sides by 2. And we end up with, cosine of 2 theta plus 1 over 2 equals cosine squared theta, right? And then, for tangent, we could... right, so we came up with this guy, came up with the other one. So if you want to come up with tangent, let's say tangent squared theta, how you can think of this is this would be equivalent to sine squared theta over cosine squared theta. And then just plug in the values that we just had. So we would have 1 minus cosine of 2 theta all over 2, all divided by 1 plus cosine of 2 theta all over 2. And then I can multiply the top and bottom by 2. So these cancel out. So what we're left with is 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. Right, which is the formula that we have, right? So we can easily come up with those formulas. Right, so with example 3, we can keep applying this formula in order to get it down to, reduce power. So example 3 is we want to write cosine to the fourth, right? Cosine x to the fourth power in terms of first powers of cosine, right? So cosine of x to the fourth power is the same thing as cosine squared x times cosine squared x, right? So if I fill this in, this would be, using our formula that we just looked at, this would be 1 plus cosine of 2x over 2 times 1 plus cosine of 2x over 2, right? Just what we looked at before. So then this would be equal to, so we have to FOIL the top, right? So this would end up being 1 plus 2 cosine of 2x plus cosine squared x, right? I have to multiply, 1 plus cosine of 2x times 1 plus cosine of 2x. Right, you should get that. And this would be all over 4. Right, so then, we still have this cosine squared part that we want to get rid of, right? So we can plug in, the power reducing formula, plug that value in for there. So this would give me 1 plus 2 cosine of 2x plus 1 plus cosine of 4x all over 2. And this is all over 4, right? So then now, to make this easier, let's multiply the top by 2 and the bottom by 2, right? The entire top, entire bottom. So we have to distribute the 2 through. So this would give me, 1 times 2 is 2, and then 2 times 2 cosine 2x is 4 cosine of 2x. And then this guy times 2, those just cancel out, right? So then we get plus 1 plus cosine of 4x. This would be all over 8. Right, and we can try to clean this up a little bit. If anything, 2 plus 1 is 3, right? So this would be, 4 cosine of 2x plus cosine of 4x plus 3 all over 8, right? Which would be good enough. But if you want to break this up in separate fractions, right, this would be, and reduce, this would end up being 1/2 cosine of 2x plus, so this would be 1/8 cosine of 4x plus 3/8, right? So I just broke this up into 3 separate fractions, right? So this part, would be 4 cosine of 2x all over 8 plus cosine of 4x all over 8 plus 3 over 8, right? And then going from there, I just simplified those fractions, right? Put them as coefficients. All right, so example 4, we want to be able to write sine x to the 4th power plus cosine x squared in terms of the first power of cosine, right? So we're gonna have to apply these power reducing formulas again, right? Keep working it until the exponent, we only have first powers of cosine. So sine x to the 4th plus cosine x squared is equal to, so I can think about this in terms of sine x squared quantity squared plus cosine x squared. Right, so then filling these in, what we would have is 1 minus cosine of 2x, so plugging in those power reducing formulas, over 2 quantity squared plus 1 plus cosine of 2x all over 2. Right, so then we're going to have to square, this fraction, right? So remember, when you square a fraction, right, like if I have a over b quantity squared, this is equal to a squared over b squared, right? I have to square the top and the bottom, right? So this would be, 2 squared, 1 minus cosine of 2x quantity squared plus, and then we'd have 1 plus cosine of 2x all over 2. Right, so let me work this part over off to the side. So if you want to look at 1 minus cosine of 2x quantity squared, you should know that this equals, 1 minus cosine of 2x times 1 minus cosine of 2x. And then we need to FOIL, right? So, take 1 times 1, we get 1. Negative cosine 2x times 1 gives me minus cosine of 2x. And then I need to take 1 times negative cosine 2x here, which gives me minus cosine of 2x again. And then lastly, these outsides gives me plus cosine squared 2x. Right, so I can simplify this to be 1 minus 2 cosine of 2x plus cosine squared of 2x. Right, so we can plug that in. Right, so then what I have now is 1 minus 2 cosine of 2x plus cosine, oops, the black won't show up there, plus cosine squared of 2x all over 4, right, because 2 squared. And then this would be, plus, and we need to get a common denominator, so what I can do is multiply this times 2 over 2, right? So I have to distribute the 2 in the top. So what that will give me is 2 plus 2 cosine of 2x all over 4, right? So now I have common denominators. So then this would be equal to, 1 minus 2 cosine of 2x plus cosine 2x squared plus 2 cosine of 2x all over 4. And then if we combine like terms, so this guy would cancel with this. 1 plus 2 is 3, right? So what we end up getting is cosine of 2x squared plus 3 all over 4. Right? So to make this easier, this would be the same thing as 1/4 times cosine of 2x squared plus 3. So then we can plug in the power reducing formula for cosine squared, and we get this would be 1 plus cosine of 4x, right, because it'd be 2 times 2x all over 2 plus 3. So then this would be equal to 1/4 times, so we could split this apart if you'd like. This would be 1/2, so split these apart in separate fractions. 1/2 plus cosine of 4x all over 2 plus 3. Right? So then what this is equal to, so distributing the 1/4 through, we would get 1/8 plus, so 1/4 times cosine 4x over 2 would be 1/8 cosine of 4x. And then plus, so then 3 times a fourth would be 3/4. Right? So then now what I can do is add these two fractions together, right? So 1/8 plus 3/4 is 7/8, right? So this would be 1/8 cosine of 4x plus 7/8. Right? And that's as reduced down as we can go, and we only have first powers of cosine. Okay, so then now we're looking at objective 3, which is applying the half angle formulas, right? So we have the half angle formulas determined, and the important thing to note here is that the sign, positive or negative, is determined by the quadrant in which the angle theta divided by 2 lies, right? So we have to, pay attention to that, right? So notice out in front, there's this plus or minus and sign in front, right? So we have to pay attention to this statement to determine if it's positive or negative. Right, so let's practice with this. So we want to find or use the half-angle formula to find the exact value of sine of 165 degrees. Right, so sine of 165 degrees is equal to the sine of 330 degrees divided by 2. Right, and 330 is one that we have on the unit circle. Right. So don't forget, all students take calculus, right? 165 is going to be in this quadrant here, right, in the second quadrant. So that's going to be positive, right? So this would be equal to positive square root of 1 minus cosine of 330 divided by 2. All right, so now we need to work that through. So 330 is going to be here, right, in the fourth quadrant. So this angle is going to be 30 degrees, which means this guy is 60. So this would be 2, negative 1. This would be radical 3. Because what we're after is cosine of 330, right? So cosine of 330 would be radical 3 over 2, right? So this would equal the square root of 1 minus radical 3 over 2. So just substituting that value in for cosine of 330, all divided by 2. So this is equal to the square root of, so I'm just going to multiply top and bottom by 2 right inside here. So this would give me 2 minus radical 3 all over 4. I'm trying to make this a little simpler. And then using properties of radicals, we can take the square root of the top over the square root of the bottom, which would be radical 2 minus radical 3 all over 2. Right? And that's simplified, right? We don't have a radical in the denominator. We can't really do much else with that. Right, so then the next one, we want to find the exact value of cosine of pi over 12, right? So, cosine of pi over 12 is equal to cosine of pi over 6 divided by 2, right? So, pi over 6 is in the first quadrant. Pi over 12 is also in the first quadrant, right? So this is going to be positive, right? So this is going to equal positive the square root of, so then using that formula, we'd have 1 plus cosine of pi over 6 all over 2. Right, we're using this formula, right? So then cosine of pi over 6, right? So if you need to, draw it real quick, pi over 6 would be here. So so this side would be 2. Let's see, this would be radical 3. This would be 1. Right? So cosine of pi over 6 would be radical 3 over 2. Right? So this would equal the square root of 1 plus radical 3 over 2 all over 2. So similarly, I'm going to multiply the top and bottom by 2 just to make this a little cleaner, right? And I'm choosing that because of that denominator under radical 3. So this would be the square root of 2 plus radical 3 all over 4. And then we can simplify this, right? This would be the square root of 2 plus radical 3 all over radical 4. Radical 4 is just 2, so this would be the square root of 2 plus radical 3 all over 2. And that's simplified. All right. All right, so now let's look at example 7. So we're supposing that sine of x equals 4/5 and x is in quadrant 1. So without using the trig or inverse functions on your calculator, we want to determine the exact value of sine of 2x, right? So what we know is that sine of 2x, so this is using the double angle formula, right, is equal to 2 sine x times cosine x. Right, so if I can figure out what sine, well, I already know what sine x is. If I can figure out what cosine of x is equal to, then we're golden, right? Because this would be equal to 2 times 4/5 times cosine of x. So I need to figure out what this guy equals. So if I draw this, right, x is in the first quadrant. Then we just label this, so sine x, so this would be opposite over hypotenuse, right? So 4/5, and then I'm not going to label this x, I'll just label it as a is adjacent, right? So we need to figure out what a is, right? Hopefully you should know by now that this would be 3, right? Because it's a 3, 4, 5, like Pythagorean triple, right? But if you need to, just solve, a squared plus 4 squared equals 5 squared. And this one we've actually done a lot, so you should know, that it turns out that a equals plus or minus 3, right? Which in this case, since we're in the first quadrant, it's going to be positive 3. Right, so in other words, we know that sine x equals 4/5, and so cosine x equals 3/5. So plugging that in, we get 2 times 4/5 times 3/5. And you can make that 2 over 1 if you'd like. So multiply straight across, so 2 times 4 is 8, times 3 is 24, and then 5 times 5 is 25, right? So then that is the answer, right? The exact answer. All right, so now I have a couple of problems left to look at. Example 8 maybe would seem a little difficult. There's some little things we have to make sure we pay close attention to. And then once we get through example 8, though, example 9 isn't so bad. It pretty much follows similarly to that. So something that we're going to need to know to look at first this is actually exercise 45 in the textbook. Right, so example 45 in the textbook, we're basically thinking through, if we have like this table, let's say this is the quadrant for some angle alpha. So we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. And let's try to think through what would the quadrant be for alpha divided by 2, right? Right, so in other words, if I have an angle alpha here in quadrant 1, what would it be if, what quadrant would alpha divided by 2 be in, right? Well, alpha divided by 2 would be half of that, so it's still going to be in the first quadrant, right? So this is still going to be in quadrant 1, right? Because the biggest angle I can get in quadrant 1 would be, less than 90 degrees, so like, let's say 89 degrees, 89.99 degrees. If I take that number, divide by 2, I'm still going to be in the first quadrant, right? And then if I think about an angle in quadrant 2, right, so let's say this is alpha, then what quadrant would alpha divided by 2 be in, right? So the biggest that I could get would be like, 179 degrees, let's say, right? It would be less than 180 degrees if we're in quadrant 2. If I take that answer and divide it by 2, right, in other words, alpha divided by 2, I'm going to be in the first quadrant, right? We would be somewhere over here for alpha divided by 2, right? So then following the same logic, if you're in quadrant 3 or 4, what you're going to be stuck in is quadrant 2. Right? So then the next rows we want to think about is, well, what's the sine of, sine alpha, And then what's the sine of tangent alpha divided by 2? Right? So don't forget, if we come over here, all students take calculus, right? So if we know the quadrant, we can figure out the sine. So sine of alpha, so I'm paying attention to just this first row, right? So sine in the first quadrant is positive, sine in the second quadrant is positive, and then in the third and fourth it's negative, right? So then next would be tangent. So tangent of alpha divided by 2. So now I'm focusing in on the second row. Tangent in the first quadrant is positive, and tangent in the second quadrant is negative, right? So then what we want to pay attention to is how these two rows match exactly, right? So in other words, sine of alpha matches the sine of tangent of alpha divided by 2, no matter where, no matter what alpha is, right? So that's a fact that we would have found in exercise 45 that we're going to need to use in example 8, right? All right. So we want to show that tangent of alpha divided by 2 is equal to plus or minus the square root of 1 minus cosine alpha divided by 1 plus cosine alpha, which is equal to 1 minus cosine alpha divided by sine alpha, right? So in other words, we already know that these two things are equal, so I want to show that these two things are equal, right? So plus minus the square root of 1 minus cosine alpha divided by 1 plus cosine alpha is equal to plus minus the square root of, so what I'm going to do is multiply top and bottom by the conjugate, right? So we'd have 1 minus cosine alpha divided by 1 plus cosine alpha multiplied by the conjugate, which would be 1 minus cosine alpha times 1 minus cosine alpha. Right, so we're doing this here, trying to do some simplification, right? It turns out that multiplying by the conjugate here will allow us to simplify things a little bit. So we still have the square root plus or minus. So in the top, underneath the radical, we have 1 minus cosine alpha times 1 minus cosine alpha. So that's just 1 minus cosine alpha quantity squared, right? And then I have to multiply the bottom through. I'm going to have to FOIL, right? Because 1 plus cosine alpha times 1 minus cosine alpha, that's a difference of squares, right? That's just going to equal 1 squared minus cosine alpha squared, which is just, 1 squared is just 1, so it'd be 1 minus cosine squared alpha, right? Well, what I'm trying to do is I'm trying to get sine in the bottom, right? We're trying to arrive to that, right? That's, that's sines here. So what I can do is we know that 1 minus cosine squared alpha is just equal to sine squared alpha, right? That's used in Pythagorean identity, right? That we've used quite a bit. So this would be equal to plus minus the square root of 1 minus cosine alpha quantity squared all over, we would have sine squared alpha, right? So what I could do is, use properties of radicals to make this be plus minus and then split it up the fraction. So this would be the square root of 1 minus cosine alpha quantity squared divided by the square root of sine squared alpha. And then what I have to be careful with here is that so if you take a number and you square it, you're automatically making it positive, right? So when you square something and then take the square root of something, you lose what the sign would be, right? So, a quick example to convince you of this is if I take, let's say -4 quantity squared and then take the square root of this. Well, this is going to equal the square root of 16, which is equal just to positive 4, right? Notice I lost the sign of what was originally there, right? And this plus or minus in the front is what's controlling the sign, right? So in other words, I don't like this is, I don't want this to be negative, right? So in other words, when I simplify this would be equal to, 1 minus cosine alpha all over sine alpha, right? If I get rid of the square roots, right? But as I was meaning, the top of this, 1 minus cosine alpha, it's possible that could be negative, right? It's also possible that sine theta could be negative, right? We know that to be true. So if one of those is negative, it's going to change the sign of the whole thing, right? Because these guys out in front, this is what controls the sign. So if this is also negative, and let's say this is positive up here, then that's going to switch that sign. We don't want that to happen, right? So what we have to do here is we want these always to be positive so they don't affect the sign. So we just put absolute values above on those, right? Just to be safe for right now. So let's kind of investigate these a little bit. So if we think about cosine alpha, this is in between -1 and 1, right? And then if I subtract cosine of alpha from both sides, what we get is -1 minus cosine of alpha less than or equal to 0, less than or equal to 1 minus cosine of alpha, right? So what this tells me is that 1 minus cosine of alpha is greater than or equal to 0 for all alpha, right? And that's by looking at this part of the inequality, right? Just focusing in on that part, right? What that tells me is 1 minus cosine alpha is always bigger than or equal to 0. So in other words, this top part here, that can never be negative, right? So in other words, what I've just shown is that I don't need those absolute value bars in the top, right? Because we were thinking through, what if that's negative, but it turns out it can't be, right? So we don't care about that. So then we still have absolute value bars around the sine alpha because we don't know what that sign's going to look like, right? But if we look at our table, right? So remember, this plus or minus is going to depend on the sine of tangent of alpha divided by 2. But remember, the sine of sine alpha and the sine of alpha divided by 2, those always match, right? So what we found is that this guy is never negative. So that's not going to affect the sign. And this guy is always going to match the sine of tangent alpha divided by 2, right? So if that's the case, we don't need this and we don't need these absolute value bars, right? Because these signs are going to come from this, right? So this would just be 1 minus cosine alpha divided by sine alpha, right? So if sine alpha is negative, we would have picked a negative here, right? So they're going to match. So in other words, this controls the sign, right? So then they're equal, right? So we found that another way to show tan of alpha divided by 2, that's just the same thing as 1 minus cosine over sine alpha, which is a little easier, right? So then the next one that we want to look at is we want to show that plus minus 1 minus cosine alpha over 1 plus cosine alpha equals sine alpha divided by 1 plus cosine alpha. Right? So this is still equal to tan of alpha divided by 2, right? If you didn't pick that up. right? So essentially, if I go back to, I think, page 4, what we're trying to do, or what we're working on through these examples, is showing these two parts, right? So we just did this one, and now we're trying to work on this one. Right, so how this one goes, so we'd have, start with the left-hand side, we'd have plus or minus square root of 1 minus cosine alpha over 1 plus cosine alpha. And then I'm going to multiply top and bottom this time by 1 plus cosine alpha. So this would give me, plus minus the square root of, so in the top, what I'm going to get is, so this is difference of squares, right? It'd be 1 minus cosine alpha times 1 plus cosine alpha. And then in the bottom, we'd have 1 plus cosine alpha times 1 plus cosine alpha, right? So this equals, plus minus square root of, so this would be, so difference of squares would be 1 minus cosine alpha squared all over 1 plus cosine alpha quantity squared. So then using Pythagorean, a Pythagorean identity, right, I can simplify the top and just plug in sine squared, right? So this would be equal to sine squared alpha all over 1 plus cosine alpha quantity squared. So then this would be equal to, plus minus square root of sine squared alpha all over 1 plus cosine alpha quantity squared, square root of that. So then this equals plus minus, so we would have sine alpha all over 1 plus cosine alpha, right? So same logic as before. We need these absolute value bars in the top and bottom, right? Because this sign is for tangent of alpha divided by 2, and we don't want the signs here to impact that, right? So if we just always take the absolute value, make them always positive, we're good to go, right? So then we already know, right, from our work last time, that sine of alpha matches the sine of tangent of pi over 2, right? So in other words, what we still have is that this guy controls the sine, right? So these and this sign here always match, right? So we don't need them both, right? So in other words, we're trading the absolute value bars for the plus minus. We just get rid of them both. So we just have sine of alpha in the top, and then we'd have the absolute value of 1 plus cosine alpha in the bottom, right? So another note here that we need to say is that 1 plus cosine of alpha cannot be equal to 0, right? Because if it is, it makes the bottom equal to 0, which makes it undefined, right? So we can't let that be 0. And we found from our work in the previous one, that 1 minus cosine of alpha, well, so we're trying to find, how would 1 plus cosine of alpha look like, right? So what we know is that cosine of alpha is going to be in between -1 and 1, right? So if I'm trying to make it look like cosine of theta plus 1, so if I add 1 here to everything, what we end up with is 0 less than or equal to cosine of alpha plus 1 less than or equal to 2, right? So cosine of alpha plus 1 is going to be in between 0 and 2. But since cosine of alpha can't be equal to 0, we could say that 0 less than cosine of alpha plus 1 less than or equal to 2, right? And this is since cosine of alpha plus 1 cannot equal 0, right? So we just threw that out. So in other words, that's always going to be positive, right? So that's always positive. So we don't need those absolute value bars, right? So this would just be equal to sine theta over 1 plus cosine, I said theta, I meant alpha, 1 plus cosine alpha. Right, so we get what we are after. All right, so last page in the notes, last example, example 10. We are told, so if sine alpha equals negative 5/13 and alpha is in between 3 pi over 2 and 2 pi, find the exact value of each expression. Right? So, just some notes here. So let me just remind us, all students take calculus, our sine thing here. So alpha is going to be in quadrant 3. Wait. No, it's in quadrant 4, right? So alpha is somewhere in here, right? And that information is what's provided here, right? It's in between 3 pi over 2 and 2 pi. So if alpha is in quadrant 3, that would mean that alpha divided by 2 is going to be in quadrant 2, right? This is the same logic as before, right? If I take any value that's in quadrant 4 divided by 2, I'm always going to be put back into quadrant 2, right? All right. So let's work this through, right? So remember the sine is going to deal with the sine of alpha divided by 2. So alpha divided by 2 is quadrant 2. So sine, this is going to be positive. Cosine is negative. And tangent's also negative, right? So just making note there of what the sine should be, right? So then, if we look at the equations, as long as we know what cosine of alpha and sine of alpha is equal to, then we can just plug those in and figure this out. So let me just draw a picture of what we have. So we know we have alpha somewhere here, right? And we know that sine of alpha is equal to negative 5/13, right? So this would be negative 5. This is, x, and this is 13. So we need to figure out what x is. So we would, use Pythagorean theorem. We'd have x squared plus negative 5 squared equals 13 squared. So this gives me x squared plus 25 equals 169. So then I can subtract 25 from both sides. We get x squared equals, 144. Take the square root of both sides, we get x equals plus minus 12, right? So we're in the fourth quadrant, so x is positive 12, right, equal to positive 12. So in other words, what I know is that sine of alpha is equal to negative 5/13, and cosine of alpha is equal to 12/13, right? So we can just plug those values in, right? So sine of alpha divided by 2 is equal to plus minus the square root of 1 minus cosine of alpha all over 2. So remember, I know that this is positive, right? So I'm just not going to write a sign because we're in the second quadrant for alpha divided by 2, so that sign is positive. So this would be 1 minus, so cosine of alpha is 12/13 all divided by 2. So this equals the square root of, so 1 minus 12/13 is 1/13 divided by 2, which is equal to the square root of 1/26, which is equal to the square root of 1 over the square root of 26, which equals 1 over radical 26. We can rationalize the denominator and get radical 26 all over 26, right, as a final answer. All right, so it's just a matter of doing the similar thing. So cosine of alpha is going to be equal to, we're going to have, plus minus 1 plus cosine of alpha divided by 2, right? But I know this is going to be negative, right? So I can just get rid of that plus. So this would be equal to the square root of 1 plus, so cosine of alpha was 12/13 all over 2. So just doing some basic arithmetic here, what we would get is negative radical, so 1 plus 12/13 would be 25/13 all over 2, which is equal to negative the square root of 25 over 26, right? Which is equal to negative radical 25 over radical 26, which is equal to negative 5 over radical 26. So rationalize the denominator again. We end up with negative 5 radical 26 all over 26. Right? So then the very last one here, right? Tangent of alpha divided by 2. That's just equal to sine of alpha divided by 1 plus cosine of alpha, right? There's no sine to worry about using this version. Because remember, sine alpha copies that sine. So this would be negative 5/13 all over 1 plus, so cosine of alpha was 12/13, right? So just plugging in those values. So now I'm going to multiply top and bottom by 13. So what we end up with is negative 5 over 13 plus 12, which equals negative 5 over 25, which equals negative 1/5. Right? All right, so that's all I have for this section. So if you have trouble with this, make sure you let me know. I'll be glad to help. Thanks.